Okay, thanks for the introduction. This is a joint work with Matt Weinberg at Princeton. So we're going to talk about a very standard setting in mechanism design. We have one seller, we have M items that the seller holds and wishes to sell, and we have N bidders or N buyers who may be interested in these items. And each buyer's valuation for a certain item is independently drawn from some buyer item specific distribution with known bounded support. And each bidder's valuation for now is going to be additive across items, which means that if I value this mic by $3 and this pointer by $4, then I'm going to value both of them by $7 together. And the seller wishes to find an auction mechanism that would yield good revenue and expectation over this product distribution. Note that I said auction mechanism, not auction algorithm. This means that we have some requirements in place to make this immune to strategic manipulations. So first of all, we require that for every possible profile of bids and for every bidder, the bidder's utility, which is his valuation of the chosen outcome minus his payment, is greater or equal to 0. And second of all, we demand BIC, what's called Bayesian incentive compatibility. So for each buyer, in expectation over all buyer types, the buyer's utility if he bids truthfully is higher than his utility if he manipulates and bids something else. This is to ensure proper input to the algorithm. And in this model, there are two standard settings or two standard objectives. First, Bayesian revenue maximization, assuming that the seller has complete knowledge of the underlying product distribution. The seller wishes to devise a mechanism or an auction with good revenue and expectation. The other standard setting that's been very popular in the past few years, revenue maximization from samples. The seller has access to polynomially many samples from the product distribution rather than to the whole product distribution. And this is a packed learning setting. So the goal of the seller is to, with high probability, learn an auction that's good up to epsilon or something like that. And the benchmark here remains the optimal auction given full information of the underlying distribution. So Bayesian revenue maximization, revenue maximization from samples has been ubiquitously seen as the next step beyond Bayesian revenue maximization. So usually we first understand how to solve the problem given the full knowledge of the distribution. We understand the structure of good auctions and then use some kind of low dimensional argument or uniform convergence argument or something to show that if we indeed learn an auction from this set or from a smaller set or something like that, there can be no overfitting. And indeed, the literature progressed like this for a single item settings, or more generally, whoever's familiar with the term single parameter settings. Meyerson, 81, seminal work that led also to a Nobel Prize for him, solved completely and exactly solved Bayesian revenue maximization for a single item. And a series of papers in recent years has used the insights from Meyerson's work from his optimal auctions to show how to learn an auction that's up to epsilon optimal from polynomially many samples. For a multi-item setting, or more generally multi-parameter setting, there's been quite a few papers that have shown how to nicely structured mechanisms can give an up to constant approximation of the optimal revenue. And in recent years, there have been some very nice papers that have used these insights in order to show how to learn up to constant optimal auctions from samples. Unfortunately, for a multi-item setting, to learn, we don't know how to learn up to epsilon optimal auctions, even from perfect information about the distribution. We know some specific things, but even for one buyer with additive valuations for two items, we don't really know how the optimal mechanisms look like. Given this, it won't surprise you that I told you that there basically are no results for up to epsilon revenue maximization from samples, because why even bother when we don't know how to solve the Bayesian setting? And nonetheless, our result is going to be here, even though we don't know how to do this. So I'd like to remind you about our notation. We have M items, N bidders, and a dependent, crucially independent valuation distribution supported on 0H. And our theorem is going to be that for every epsilon and delta, the sample complexity of learning with probability 1 minus delta with high probability, in IR an epsilon BIC, we're going to get to this epsilon soon, auction that maximizes revenue among all such auctions up to an additive epsilon is polynomial in all of the parameters of the problem. This is the first learning result for up to epsilon in a general multidimensional case. So we said that Bayesian incentive compatibility means that my expected utility if I bid truthfully is at least as high as my expected utility if I try to manipulate. So epsilon BIC means that, well, maybe I could gain 1 cent in utility if I manipulate, but not more than that. I'd like to emphasize that this is for a computationally unbounded learner. This is an information theoretic result that says that so many samples hold within them enough information to identify a good auction. We don't have an efficient algorithm to do that. And the proof, as I said, assumes nothing regarding the structure or dimensionality of optimal revenue auctions or even approximately optimal revenue auctions, because frankly, we don't know anything that we can use in this sense. And this, I described the model for you for additive valuations, but it holds even far beyond. So let's talk about that for a moment. So the most general case in which we can prove our result is for a general outcome space. Usually people talk about the multi-item outcome space. So there is an indicator for each item and each bidder, whether that bidder wins that item, and no item can be won more than once. We're talking about a completely general outcome space. We'll see some crazy examples soon. And all we require that each buyer's valuation function be parameterized by M values. So in the case of the multi-item case, then the M values are exactly the values for each of the items. But we can have any valuation functions parameterized by M values and log as really these values are drawn independently. And as long as the valuation function is Lipschitz continuous in these values. By that I mean that if I fudge the value of one of these parameters by at most epsilon, then the valuation of any outcome would move by at most L times epsilon. So these are quite mild conditions. They encapsulate all of the standard additive unit demand, additive subject to constraints for whoever is familiar with this. Settings, all of them with Lipschitz constant 1. They even encapsulate not so standard stuff like several natural sub-additive and even super-additive valuations, such as the right shoe is going to be valued by VJ as long as I also get the left shoe, otherwise it's worthless to me. And also kind of crazy stuff like X being the outcome space being the set of movies we have to choose from, and the parameters are my affinity to action films, drama films, horror films, comedy films. You can see how this is also continuous in this. So we can do this also without a problem. And note that independence and Lipschitz really should be here, because without Lipschitz, we cannot rule out some nasty standard tricks like bit interleaving to condense many parameters into a single parameter. We need some kind of continuity to really have a meaning for the number of parameters. And so we have epsilon BIC in the general case. For special cases, we have stronger corollaries. So for a single bidder, we can learn an exactly IC auction. This is also new. This should be compared to Dormi et al. From 2014 that shows that for correlated distributions, even additive, you need exponentially many samples. So we show that if distributions are independent, even in our very general model, polynomially many samples suffice. And for single parameter settings, these have been very heavily studied in the past few years. Usually the standard model is that the outcome space is what I told you earlier. Each bidder has an indicator that says whether they won or not, and the valuation is simply VI times their probability of winning or their amount of winning. So here we managed to, using a straight corollary of our analysis, we managed to give match the known result by learning incentive compatible and doing it efficiently. We actually have slightly more general outcomes than the state of the art, but crucially, we treat single parameter optimization almost as a black box here, as opposed to previous analysis that relied on very minute details of the structure of optimal auctions for single parameter settings. So our proof strategy is going to be as follows. We're going to assume access to an oracle that can solve the Bayesian optimization problem precisely for explicitly given discrete distributions. This is only a matter of computation. There's no magic here. The oracle has all of the information available to it. But we're going to assume nothing about the structure of the output of the oracle. And using this oracle, we're going to explicitly construct our learning algorithm. And in fact, on the way, we prove a general meta theorem, a black box reduction, if you wish, that says if for some constant c, there exists an efficient algorithm that can solve Bayesian revenue maximization up to a constant factor c for an explicit finite product distribution, then there exists an efficient learning algorithm that can match this constant c up to an additional additive epsilon that can pack learn for the exact same setting using polynomial in many samples. So you reduce from Bayesian revenue maximization with precise instead of compatibility to learning with epsilon instead of compatibility. So our learning algorithm is going to be, it's going to look similar in nature to the single parameter algorithm of Devanur et al. From Stokes-Texin, but our analysis is going to be completely different. So we're going to start with the samples. So we have each sample is n times m values, each of them sampled from better i's distribution for good j. So we have n times m bitter good combinations. Then we're going to mix and match, and we're going to define the empirical distribution over all of the samples that match a certain bitter and a certain good, rounded down to a multiple of epsilon. Remember this is going to be important. Then we're going to take the product of these empirical rounded distribution to obtain the rounded empirical product distribution. We're going to feed this to our Bayesian optimization oracle depicted here by my son last year when he was 8 months old next to the oracle's temple in Delphi. This is going to be important soon. Keep this in mind. And then this mu is an auction for bids that are multiples of epsilon. Our final auction is going to be an auction that rounds the bids to multiples of epsilon and then runs the output of the auction. And I'd like to remind you that we know nothing about the structure of the output of the oracle, much like the structure of the syllables uttered by my son when he was 8 months old. You can see where this is going. So even given that, and we also know that the optimal auctions have very high dimensionality. So how come when we cannot know nothing about the structure, but we know that it's high dimensional, how come we can rule out overfitting? That's the main challenge of our analysis. So this is the same algorithm of structured it geometrically a bit different for the analysis to follow. And first thing I'd like to do is to think about this rounded empirical distribution not as being sampled and then rounded, but as being rounded and then sampled. So we're going to have, this is going to be the true distribution rounded to multiples of epsilon, and we're going to think about the samples as coming from this. And I'm going to copy the output of the oracle here as well, because we're going to reason about its revenue from here and its revenue from here. And first of all, note that by definition, mu is big and optimal for the samples, right? That's the definition of the oracle. And we're going to claim now that it's almost optimal for the true rounded distribution. So we're going to first claim that mu attains similar revenue on the empirical and on the real distribution. This is the challenge here. How can we do this without knowing what's the structure of mu? Well, we claim that it's enough to take a union bound over so many random variables, each corresponding to a different mechanism that may be output by the oracle. And how come that's the case? Well, we claim that there aren't too many inputs that we may feed into the oracle. If we're talking about product distributions over multiples of epsilon, then we have nm bidder item combinations. Each of them has h over epsilon bins. Each bin may have between 0 and s balls in it, where s is the number of samples. So we're going to take a union bound over that, which means that for a single variable, we're going to need convergence with we're going to need non-convergence with probability at most delta over the number of variables we're going to union bound over. and which means that we need the number of samples to be roughly the log of 1 over this, which is poly in the parameters of the problem times log s. So we have here a hypothesis class that grows intrinsically with the number of samples, but grows moderately enough with the number of samples, only grows like log s, so that s that's polynomial in the parameters of the problem is going to give us an equality between s and between poly stuff times log s. So we can do, by taking so many samples, we have enough samples to do this union bound and get what we want. Note that so far I've shown you that mu attains similar revenue over the empirical and the real bounded rounded distributions. I haven't told you why there couldn't be any better optimal distribution for here that gets much higher revenue that could possibly be attained here. So I haven't completed the argument for why mu is epsilon optimal for this. So let's think about this auction for a second, the auction that's going to be optimal for the rounded true distribution. We know by definition that mu attains higher revenue over this for the rounded, for the sample distribution. We're going to claim that mu gets approximately not more than epsilon less than the revenue of this also for the real distribution. So we're going to claim that mu and also opt epsilon attain similar revenue here and here. And crucially, while our learning algorithm cannot hope to identify this distribution, it's a well-defined mathematical object independent of the samples. So all we need to do is add another variable to our union bound. So +1 here, +1 here, still polynomially many samples suffice. So nice, we have, so we've shown this, we've shown that this auction is almost optimal for this. What about almost big? Right, we have to show that this auction is almost instead of compatible for here. So we're going to claim that mu and epsilon, opt epsilon not only have a similar revenue over these two distributions, but also have a similar reduced form. The reduced form of a mechanism is defined to be this set of random variables, my expected utility when I bid something, and my true distribution is something else. This set is parameterized by my index and my true valuation and the valuation that I bid. And I'd like to remind you, this is well known, that the constraints for Bayesian incentive compatibility and even epsilon Bayesian incentive compatibility only depend on these random variables. So we're going to do our union bound not only over one variable per auction, but over the revenue plus all of the variables in the reduced form for each of these auctions. This looks like a lot, but when we propagate it here, still poly many samples suffice. So that's going to complete our argument for why mu is almost big and almost optimal for the rounded distribution, and it's straightforward. I'm not going to do it here to show that if we give up another epsilon and instead of compatibility, then this modified mu will get the same revenue for the real distribution. That completes our general proof. For special cases, for one bidder, there is a known reduction 10 years old from epsilon IC to IC for one bidder. So we can, that loses only poly epsilon revenue, only negligible revenue. So we can apply that, immediately get a precisely IC auction. I'd like to remind you that this has not been known yet, even this corollary, this special case. For single parameter domains with the structure that I described so far, we have a much more mature understanding of the structure of optimal auctions, much like the words iterated by my son now when he's 2 years old. And this allows us to show that rounding, in fact, does not even epsilon hurt incentives. We can do that all together to show that we precisely learn a precisely IC auction. We don't even lose an epsilon and IC anywhere along that diagram that I showed you. Moreover, optimization can be efficiently implemented. That's well known. So by our reduction, we can efficiently implement the oracle, and we obtain efficient learning for precisely IC auctions for general outcome spaces. And as I told you, this is slightly more general outcome spaces than the state of the art, even though they have some better polynomials in there. Even though we treat the optimization algorithm almost as a black box, we only need it here and here, as I told you, while previous analysis relied heavily in each step of the proof of minute details of the optimization algorithm and its output. So further research, getting rid of the epsilon and the epsilon BIC, given an IR and epsilon BIC auction for some product distribution, even in an additive multi-item setting, make it as simple as you wish. Is it possible to transform an IR and epsilon BIC auction into an IR and precisely BIC auction with negligible revenue, so only stuff that goes to zero with epsilon, fast enough, with negligible loss, using polynomially many samples from the product distribution? There's a known beautiful work on epsilon BIC to BIC reduction from samples by Dormi et al. From stock 17, but it requires the number of samples that's polynomial in the size of the type space, which means that it's exponential in the number of items. We don't know how to exploit independence to get polynomial in the number of items. This reduction is for welfare maximization rather than revenue, but we find this open question equally interesting in both scenarios. It would be great if someone from the audience could find an ingenious way to handle this. That's all I have to say. Thank you. Yeah. So the idea is, for this counting argument to work, I need the input to the oracle to be a product, the empirical input that I feed to the algorithm to be oracle to be a product distribution. Otherwise, there are just too many. We get something that's doubly exponential, and that doesn't work. So, yeah. And then there's, I should add, and then the union bound that the concentration Bobby. Okay. The concentration inequality that we're using to go from the real distribution to the sampled distribution, made product distribution, is also a tailored concentration inequality for this case. It's due to Yakov et al., Babichenko et al. From a paper from a few years ago. Okay, thank you very much.